This is lecture number 5. So in that we have seen Gauss law applications for finding D and hence E, okay, for spherical shells, okay, and also we have seen charged sphere, uniformly charged sphere, and also infinite line charge, and also we have seen infinite sheet of charge. So finding D and hence finding E, for these items we are discussed, and we were discussing about the coaxial cylinders. So determination of flux density and hence the field intensity in a given coaxial cables we were discussing about, and this is what we were discussing about. So coaxial cable, that means there will be two coaxial cylindrical conductors, and each of length L, and inner one is a solid cylinder of radius R1, and outer one is also a hollow cylinder of radius R2 with negligible thickness. Okay, so we have we have this thing that is a radius R1 and R2. So R1 happens to be your radius of the inner cylinder, and R2 happens to be the radius of the outer cylinder. And length of the cylinders are same. That means L is the length of the cylinder. This is what we have discussed, and we have identified three regions here. So region number 1 is supposed to be inside the cylinder 1, that is the inner cylinder. It is R is less than R1. So you will be requiring to find the flux density and hence the field intensity inside the cylinder whose radius is R1. And another region, R is greater than R2, that is outside the outer cylinder whose radius is R2. So you'll be required to find the flux density and hence the electric field intensity outside the outer cylinder whose radius happens to be R, that is equal to that is greater than R2. And one more region where R is greater than R1 and less than R2, that is in the space between the two cylinders. So we were actually solving the expressions for flux density and field intensity in these three regions. Okay, so in all these three regions, what is that you are supposed to do? So you are supposed to do, or you are supposed to assume a Gaussian surface, and then find the total or amount of flux which is emanating the Gaussian surface. So that is equal to the charge stored or charge inside that Gaussian surface. So using this charge, you can find D, and then you can find E. So this is what the flow. First check whether there is flux. If there is flux, there will be some charges inside, and due to the charges, there will be some flux density, and due to the flux density, you will be having some field intensity. So this is what we have discussed so far. And come back to the first case 1, where Um, you can check out the last class derivation where we have taken the region as between the two cylinders. That means the inner cylinder and outer cylinder, between them we have got one point P. That point P is taken as like this. This is the point P, what we are discussing about. And using that point P, we have just assume a Gaussian surface. That Gaussian surface is nothing but a Gaussian cylinder. Gaussian cylinder. It has got three faces. One is the circular cylindrical face, and another one is the top as well as the bottom surface. The flux can emanate in across these three surfaces. Okay. Yes. So as we know, the flux density and the field intensity will be in the same directions. That means they are parallel to each other, and the flux density and the field lines are or will be radially outwards. So as a result, the flux lines or the field lines will be perpendicular to the axis of the cylinder. Will be perpendicular to the axis of the cylinder. So as a result, the total flux phi is equal to phi1 plus or phi surface plus phi top plus phi bottom. Okay, so we are assuming that the flux, the charges are uniform across the inner cylinder. So as a result, there will be some flux lines which is crossing this Gaussian surface, which will be radially outwards. That is a basic fundamental assumption, radially outwards. And across small surface like this, the D and E will be parallel to each other. So the angle between them is 0. As a result, you will be having the flux as D vector into ds vector. Okay, and also we have discussed that there will be no flux lines emerging out of the bottom surface as well as the top surface, because so they will be what parallel to the axis. There will be what parallel to the axis of the cylinder, and you will not be having any flux lines across the top surface or the bottom surface, because the normal to the normal to the surface is like this, and which will be at a 90-degree with respect to the field lines. So the angle between them becomes equal to 90-degree. So cos 90 is 0. Therefore, the dot product of flux density component and the surface vector component becomes 0. Therefore, there will be no fluxes crossing through the top surface as well as the bottom surface. Therefore, this component is 0 and this component is 0. The total flux is equal to only the flux crossing through the surface. Okay, so that is nothing but um, integration of d1 vector into ds vector. Okay, so we shall just recall what we have done in the last class. Same thing I'm doing here. So it is integration of d1 vector into ds vector. So d1 vector and ds vector. So d1 into that magnitude component, means the d1 is a magnitude, and ds is also the magnitude, and whose unit vectors, it is ax cap or an cap into n cap is what 1. So we'll be getting only this part. So d1 into ds. Okay, so this is the total flux. So, and d1 is nothing but your constant. The constant across the surface because we assume that uniform charge distribution over the inner cylinder. Therefore, D1 is constant, and ultimately you'll end up in getting as ds, that is surface area of the cylinder of curved portion. So d1 into 2 pi into r into l. This is the area of the curved surface of the cylinder. So this is the expression what we have discussed in the last class. d1 into 2 pi into r into l. Okay. Yes. As a result, so you can assume that d1 as d because it is the only flux density available, because there is no flux density available at the bottom as well as the top. So you can replace that by what? D into 2 pi into R into L. Okay. So this is what the flux, total flux crossing the Gaussian surface. Okay. Now using this, we can find out the charge. So your total flux is equal to what? D into 2 pi into R into L. That will be equal to the amount of charge enclosed. So the amount of charge enclosed, so it is enclosed by the Gaussian surface. So this is nothing but total charge enclosed by the Gaussian surface. This is equal to total charge on the inner cylinder, on the inner cylinder. Okay. So on the inner cylinder, that is nothing but length of the cylinder, and that means you can find out the total charge using its density as well as surface density as well as the area, that is rho s into ds of the inner cylinder. So that is equal to rho s into ds is 2 pi r1 into l. So this is your surface area of the inner cylinder. Okay, don't get confused with this 2 pi rl. This is surface area of the Gaussian surface, and this is nothing but 2 pi r1 into L is the surface area of the inner cylinder. Okay, so therefore, so your flux is equal to what? The charge enclosed. So we can get a solution like this. So so D into 2 pi RL is equal to rho s into 2 pi r1 into 2 pi r1 into L. So we know D. D is nothing but epsilon naught into E. Okay, 2 pi RL, that is equal to rho s into 2 pi r1 into L. Okay, so ultimately we'll be getting epsilon naught into E into R is equal to rho s into R1. So we also know that rho s is equal to total charge Q by area of that curved part. It is Q by 2 pi R1 into L, that is equal to 1 by 2 pi R1 into Q by L, that is equal to 1 by 2 pi R1 into rho L. So rho s is equal to 1 by 2 pi R1 into rho L. So if you just substitute like this, you will end up in getting expression for E as rho L by 2 pi epsilon naught into R. So this is the electric field intensity between the regions, okay, R1 as well as R2. Okay, so if the vector form, so it is nothing but rho L by 2 pi epsilon naught into R into A R cap. Okay, so this is what we have discussed in the last class. Just I've revised this one. Yes, next one. So just check out here. So where exactly the Gaussian surface now in this case? Can anybody let me know where exactly the Gaussian surface and what is that we have assumed?
Sir, R is less than R1.
Yes. Here the region is R is less than R1. That means I am considering a point. This point P is assumed to be inside the inner cylinder. Therefore, the Gaussian surface is inside the inner cylinder. So what is the conclusion here? Can the Gaussian surface enclose any charges?
No, sir.
No. So because Gaussian surface cannot enclose, because it is inside the inner cylinder, all the charges are on the inner cylinder. Therefore, it cannot enclose any charges. Therefore, the flux density, the flux emanating or crossing the Gaussian surface is zero. Therefore, charge enclosed is zero. Therefore, D vector is zero. As a result, E vector is zero. That is inside the inner cylinder or the coaxial cylinder is having radius R, the R1. So it is in terms of what? Zero. Yes. Next, the last one. So the Gaussian surface is assumed to be covering the outer cylinder. That means the point P is here. The point P is here. Therefore, so it is covering both the cylinders, the inner cylinder as well as outer cylinder. Yes. Now what is happening here? So your R is greater than R2. So what is happening? So can Gaussian surface enclose any charges here? Yes, it encloses charges due to inner cylinder as well as the outer cylinder. But those charges are opposite in nature. Therefore, the total charge enclosed is zero. Just check here. Over the inner cylinder, the charges are plus, and over the outer cylinder, the charges are minus. Okay, that means the total flux over the Gaussian surface is equal to what total charge enclosed, but the charge on the inner surface of the cylinder are equal and opposite to the charge on the outer surface of the cylinder. Therefore, the total charge is equal to what? Zero. So therefore, you will not be having E vector that is equal to zero, because flux will be zero, means flux density will be zero. As a result, no flux lines. Clear? So what is that you have to check for here? The cancellation of the charges, which are equal and opposite to the charge on the outer surface of the inner cylinder as well as the inner surface of the outer cylinder. Okay, so these things are very critical in identification of the flux density across different points in a system. So what is the conclusion here? What is the conclusion here? So no field surrounds a coaxial cable. no field surrounds a coaxial cable, and no field exits within the inner cylindrical core. So there will be no field in the innermost core and the outermost surface. That is the point here. So there will be no field in the innermost core and the outermost surface. So this happens in all transmission lines. In all transmission lines, which uses coaxial cables. Okay. Yes. So we have completed 4 applications here of Gauss law. We have completed spherical shell, charge sphere, infinite line charge, infinite sheet of charge, and coaxial cylinders. So you might expect any problem based on these things. So you'll be given the scenarios, you'll be given the values, you will have to use the logics, and you'll have to recall, or you'll have to derive respective equations, so that you can solve the problems. Okay. Yes. Now just take down the first problem here. Very straightforward problem, and try to solve. Yes, very straightforward problem. So what is that given here? You are given a charge, point charge of 30 nanocoulomb. It is located at the origin. You are required to find flux density and field intensity at point 1, 3, minus 4. Okay. Yes. So I'll just help you out. I'll not solve the complete problem. I'll leave it to you. So yes. So Q is given for you, 30 nanocoulomb, and P point is given 1, 3, minus 4, and Q is at 0, 0, 0, that is origin. So you are supposed to find field intensity at this point and flux density at this point. Okay. Yes. So we have got relationships now. D is equal to epsilon times into E vector, and E vector is equal to, due to point charge, Q divided by 4 pi epsilon naught into dAp square into AR cap. Okay, this is what we have got. That is U cap AP, you can call it as, or it is nothing but I'll call it as general sense U cap AP. Okay. Yes. So you are required for solve for this U cap AP first. u cap AP, that is AP vector divided by magnitude of AP vector. And after having found out u cap AP, you can find E vector. And after having found out E vector, you can find this B vector. Okay. Yes, this is the flow. So first step is to find AP vector, and next to find magnitude, and then u cap AP, and like this. Yes. Anybody have solved the problem? Hello? Anybody have solved the problem? Zishan? Hello? Hello? Chandramohan? Hello?
Sir.
ಸಾಲ್ವ್ ಮಾಡ್ತಾ ಇದೀರಪ್ಪ?
Sir, ಮಾಡಿದೀನಿ ಸರ್.
ಹೇಳಿ ಆನ್ಸರು.
Sir, vector E is equal to
ಹಾ
2.03 AX cap
2.03 1 second.
AX cap
ಹಾ ಕರೆಕ್ಟ್
plus 6.09 AY cap
ಕರೆಕ್ಟ್
minus 8.136 AZ cap.
ಕರೆಕ್ಟ್ volts per meter.
Sir.
Yes. D vector.
Sir, 1.8 into 10 power minus 11 AX cap,
Okay.
5.4 into 10 power minus 11 AY cap.
Okay. 5
Sir,
point. 5 point.
sir, 5 point, sir, 5.4.
Into 10 power minus 11 ಅಲ್ಲ?
Sir, minus 11.
Okay. Minus
11, sir, minus
7.2
7.2 into 10 power minus 11.
AZ cap.
Sir.
Okay. So this is the solution. Correct answer. Okay. Everybody has to solve. Otherwise, you will be the losers. See, I'll not be able to monitor here from online. It is impossible for me to monitor each and everybody's book here. So it is your responsibility. Why I have began with a simple problem, because you should recall this one. You would have forgotten this one, how to solve electric field and how to solve electric flux density and how to find unit vector. Okay, that's why I started with this problem, so that you will brush up the basics to how to solve for a unit vector. Okay. Yes. Next problem. Take down this problem. Yes. Now Rishabh is here.
Yes, sir.
Yeah, go ahead. How to solve this one? What is given for you?
Sphere, sir.
A dielectric sphere is given. Okay.
Yes, sir.
Next, what is the radius of the sphere?
5 centimeter.
Yes, it is 5 centimeter, 0.05 meters. 0.05 meters is the radius of the sphere. And what is the density? Density of the charge on the sphere? It is rho v. Rho v is given. So it is given to be 1.2 into 5 minus 2 pi microcoulomb per meter cube. So this is the charge density. Charge density on the sphere is given. It is 1.25 minus 1.2 into 5 minus 2 to 10 power minus 6. That is supposedly minus 1.54 into 10 power minus 6. Okay. So here you have to observe rho v is not depending on any parameter. That means rho v is neither dependent on the radius nor on any parameter. That is why it is a constant. That is why it is a constant microcoulomb per meter cube. Okay, if rho v did contain any variables like x, y, z or radius, angle, theta, that means you will have to check for its variations and limits. Then you have to include in the integration or respective differentiations. Okay. Yes. So this is what we have given for you. Okay. So what is that you are supposed to find out, Rishabh?
Electric flux density, sir.
Yes. D vector you have to find out. Yes. Next. Also. That's all. Yes. D vector you have to find out. At which point you have to find out? At
100
the
meter
point
away
P.
from center.
At point P, 100-meter away from the center of the sphere. This is the center of the sphere. So 100-meter away like this. Let this point be like this, and this is the distance is 100 meter. So you are supposed to find D at this point. Okay. Yes. So how to find D? So to find D, so what is that you require? The the relationship what you are having, that is D is equal to epsilon naught into E vector. You require to find E, so that E is equal to Q by 4 pi epsilon naught DAP square into U cap AP. So this is what actual expression for the electric field intensity. And after having found out electric field intensity, you can find the D vector. This is what is required. Okay. Yes. Now the unknown quantity here, it is nothing but Q here. So we know D, okay, that is 100 meters given. So you can find directly the E vector, that is a magnitude, that is nothing but Q by 4 pi epsilon naught DAP square. Okay. From this E you can find D. So first you have to find Q. So what is Q? Q is in terms of charge density. So what is the expression for charge density? Q in terms of charge density?
Rho v into v.
Yes, it is nothing but integration of rho v into dv. So rho v is constant. Okay, dv is also nothing but the constant because the charge density is independent of the terms of volume parameters. Therefore, Q is equal to rho V into V. Perfect. So it is nothing but minus 1.54 into 10 power minus 6. What is volume of the sphere? Expression.
4 by 3 pi r cube.
Yes, 4 by 3 pi r cube. So you know the radius of the sphere. Substitute and you'll get Q. Q is supposedly now 6.45 into 10 power minus 6 into 5 into 10 power minus 2 whole cube. So Q is equal to 8 into 10 power minus 10 coulombs. Therefore, you'll get E and hence you'll get D. That is the solution. Understood, Rishabh?
Yes, sir.
Yes. Shubha Mangala. Hello. Shubha Mangala. Desai.
Yes, sir.
ಅರ್ಥ ಆಗ್ತಿದ್ಯಪ್ಪ?
ಹಾಂ ಸರ್,
Hello.
ಅರ್ಥ ಆಗ್ತಿದೆ ಸರ್.
Okay. Vaibhavi,
Yes, sir.
following?
Yes, sir.
Yeah. So what is the answer for E now?
Sir, 1 minute.
Yeah.
Seven point two into 10 power minus 4, sir.
7.2, correct. 7.2
Into 10
into
power
10
minus
power minus 4 volts per meter. Correct?
yes, sir.
So this is the solution for E, and then you can solve for D. Okay? Yes.
63.74
63.74
into 10 power minus 16
minus 16. What is the unit of flux density?
coulomb per meter.
Yes. Meter square. Okay. Yes. Next problem. So I want Sanjana YK. Sanjana?
Yes, sir.
Yeah. Just go through the statement of the problem. Yes, what is given, madam?
Sir, 3 concentric spherical surface having radii.
Yes, once again. 3 concentric spherical surfaces. So we have solved this one, correct? So there will be
Yes,
3 spherical surfaces like this. Okay.
Sir, radii 3 centimeter, 5 centimeter, 7 centimeter respectively.
Yes. Okay. So this is 3, this is 5, and this is 7. Next.
Sir, charge density.
Yes, charge density is also given. So respective, that means spherical surface having radii 3 radius 3. So it is having 200 as charge density and minus 50 as charge density, and rho x as charge density of the sphere having radius 7 centimeters. Correct? Any doubts here? Sanjana?
No, sir.
Yes. What is that you are supposed to find?
Sir, d vector and d vector at radius is equal to
Ah.
2 centimeter.
And
Sir, radii is equal to 4 centimeter and radii is equal to 6 centimeter.
yes, you just have to find out the d vector and e vector are 3 points. So at radius is equal to 2 centimeter. That means inside the smaller sphere. So this is P1 and 4 centimeter between the innermost sphere and the second sphere, that is P2, and 7 centimeter, which is outside this one, the outer sphere. So that is within the sphere, that is correct, within the last two spheres, between the last two spheres, like this, P3. Okay, so P1 happens to be the point inside the innermost sphere having radius 3 centimeter and having a P2, that is between the first sphere, innermost sphere, and the second sphere having radius 5 centimeter, and the last one is a point P3, so which is between the last two spheres having radius 5 centimeter as well as 7 centimeter respectively. Okay, yes. So now what is the inference you can draw now? Can somebody let me know? So ಎಲ್ಲಿ ಡೆನ್ಸಿಟಿ ಇರುತ್ತೆ, ಎಲ್ಲಿ ಡೆನ್ಸಿಟಿ ಇರಲ್ಲ, ಇದ್ರೆ ಯಾವ್ಯಾವ್ದ ಸ್ಪಿಯರ್ ಇಂದ ಇರುತ್ತೆ? Which spheres contribute densities at what points, and which point does not have any density?
Sir, inner two circles irutte.
Yes, the first point. So will you be having the flux density and field intensity, okay, at P1?
Yes, sir.
Yes or no?
Yes, sir.
Irata iralva?
ಇರಲ್ಲ ಸರ್.
Yes, you will not be having flux density and field intensity at point P1 because the statement, it is inside the innermost sphere. So the sphere will not enclose any charges. Therefore, you will not be having any flux. Therefore, you will not be having any flux density. Therefore, you will not be having any field intensity. Is it clear? So that point is inside the innermost sphere. So, and that sphere will not enclose any charges. Therefore, the flux density is 0. Clear? Any doubts here? We have derived. So you have forgotten, I guess. You should not forget those concepts. Okay? So application of Gauss law. So the Gaussian surface at point P1 is not enclosing any of the charges. Therefore, you will not be having any flux density at that point. So this is the Gaussian law. Okay? Yes. Next, come back to P2 now. At R is equal to 4 centimeters now. That means P2 is at 4 centimeter from the center of the sphere, concentric spheres. Okay, so 4 centimeter from center of the sphere. So what exactly, first question, whether there will be flux density or not?
Yes, sir, present.
Sir.
Hello? Yes, there will be what? Flux density. And which sphere is contributing to the flux density?
So both radius 3 and 5 centimeters.
No,
Innermost
the flux density.
innermost sphere.
Yes, the flux
So
density is contributed by the
3.
innermost sphere only. Why? Why? Because the point is between the two spheres, and the flux lines will be emanating from this innermost sphere. Okay, and the sphere which is marked red color will be emanating the flux lines outwardly, not inwardly. Correct. Therefore, the point P, but the point P2 will experience flux density due to the sphere of radius 3 centimeter alone. Okay, because the charges enclosed by that sphere of radius 3 centimeter is only contributing to the flux density at point P2. Is it clear? Got it? Again,
Yes.
it is first principles. Now I want to find that value, that is E vector is equal to, I'll write directly the expression rho s into, it is R1 square divided by epsilon into DAP square, okay, into, I'll read as AR cap, okay. Yes, R1 is the radius of the sphere which is contributing to the flux density, that is nothing but 3 centimeter, that is 3 into exponential minus 2, okay. Yes, this is E at P2. So what is the DAP? DAP is the distance between the point, okay, that is nothing but from the center, so it is 4 centimeters, okay. Yes, radius of the sphere, and R is what, the DAP is what, say 4 centimeters is the distance. Yes. Now, next point. So point P3, come back to point P3. Yes. Will you be having any flux density at P3?
Yes, sir.
Yes,
Yes.
sir.
Yes. Yes. Now, and which spheres are contributing to the flux density at point P3?
So both the inner circles.
Exactly. The sphere of having radius 3 centimeter and the sphere having radius 5 centimeter will be contributing to the flux density at P3 because they will be emanating the charges or the flux lines towards that P3 point. Clear? So obviously you will be having the flux density at P3 due to two spheres, one having radius 3 centimeter and another one having radius 5 centimeter. Is it clear? And you will not be having any flux density due to the outermost sphere because the flux are assumed to be moving outwards, not inwards. Clear? Yes. So just find out two fields and add it, you will get the answer. So E at P2, I suppose, right? P3. E at P3. So E due to sphere of radius 3 centimeter. Find out. Let this be first point. Second point, E due to sphere of radius 5 centimeter. So add it together, you will get, for example, this is E1, this is E2. Okay, you got the formula directly. Substitute E1 plus E2, that is equal to what? E. That's all. Shubhamangala, Zishan, understood? Vivek,
Yes, sir.
okay. Yes, anybody solved the problem? Use the same formula. Use the same formula. That is nothing but rho s by 2 epsilon naught into yes. I lost the file again. No, someone did the mistake. Yes. So I'll write the answers. E1, the total E I will write is E1 plus E2, that is equal to 1.7255 exponential 6 volts per meter. Okay, AR cap. This is the solution. Yes. Next, last part of the problem. Find rho x. Find rho x if d is equal to 0 at 7.32 centimeters. Find rho x if d is equal to 0 at 7.32 centimeters. So what is that you have to do? It is given as what? Flux density is 0. So flux density is 0 on the outside of the outermost shell. This is the outermost shell, and this is the point. Okay, and this is nothing but 7.32. At this point, d is 0. At this point, d is 0. You are supposed to find rho x, the charge density of this point, of this sphere. Okay, yes. So you just have to find the value of the charge density such that at this point the flux density is 0. Okay, so what is that you do? You find d1, you find d2, you find d3. Okay, add all those things and equate it to what? 0. And in this d3, you'll be having what? Unknown function, that is rho x. So solve for rho x, then you will get the answer. So that is nothing but minus 11.22 microcoulomb per meter square. Okay, so you can either find E1, E2, E3 and then find D1, D2, D3, or you can directly find D1, D2, D3 and add them and equate it to 0. And D1 and D2 will have the flux density, charge densities. Okay, and D3 will have charge density as rho x. Solve for the unknown term, that is rho x. Okay. Yes. So this completes this problem. Any doubts up till this point? You can ask me. Okay, if it is clear for you, please type 0 on the chat box. Okay. What I will do, so I will just stop at this point. This completes the application of Gauss law, and next class tomorrow, so I'll be starting with the divergence theorem. I'll be starting with divergence theorem. So tomorrow during lab hours, I'll be engaging the class. Okay. So you'll be having lab hours, during the afternoon. So I'll be engaging the class from 2:30 to 3:30. Okay. So that will be my additional class. So I'll be covering the divergence theorem. Okay. So divergence law and Maxwell equation. Very important. So what all I have solved so far and what all I have discussed so far, you might expect theory questions as well as problems during the examination. Okay. Yes. So I'll stop at this point. You can exit for the next class. Thank you.